Alright, this is the notes for section 6.4 where we're going to look at the graph y equals ax squared plus bx plus c. And really what that means is we're going to look at another form, and we've kind of touched upon it in 6.1, but we want to formalize it a little bit, and that is the idea of the standard form for a quadratic equation. Okay, and what we know about the standard form for a quadratic equation is we write it like this in descending order by the power on the independent variable. So in this case it would be, if x is our independent variable, that would be y equals ax squared plus bx plus c. Now any equation written in vertex form, like what we looked at in 6.3, can also be written in the standard form. So we're going to find that there's some things that are much easier to find about a parabola when we write them in vertex form, and other things are going to be much easier to find out about in standard form. Alright, so for our first example, what I'd like to do is I'd like to look at the idea of taking something that's in vertex form and changing it to standard form. So I'm given this equation right here this is in vertex form. You'll notice y minus k equals a times x minus h quantity squared. And we want to rewrite it in standard form. So we want to get it to look like this. Okay. So what I have to do is I have to follow my order of operations. So according to my order of operations, and this is one place where people make a lot of mistakes, is that I have to take care of that stuff first. So I'm going to use my binomial square theorem to help me do that. So I'm going to rewrite this whole thing as y plus 5 is equal to 4 times, now I'm going to square this out, so x squared plus 2 times x times 3, which would be 6x, plus 3 squared, which is 9. Now the next thing I want to do is I want to use my distributive property and take the 4 and distribute it to all three of those terms. So I'm going to rewrite this as y plus 5 equals 4x squared plus 24x plus 36, and then finally I'm going to subtract 5 from both sides, and I'm going to put it right underneath the constant because that's going to be where I can combine like terms. These can cancel out and I'm left with y equals, and then it's going to be 4x squared plus 24x. Now this stuff can be simplified to plus 31. And this would represent that answer in standard form. So what I want to show here is that you can go between vertex form and standard form fairly easily. So next what I'd like to do is take a look at the parabola congruence theorem. And it just says the following: the graph of an equation y equals ax squared plus bx plus c, in other words standard form. One thing that we have to be aware of is that that a value here is the same as this a value here. And it just says that, hey, this parabola here will always be congruent to this parabola here. In other words, if I have y equals ax squared plus bx plus c, it will always be congruent to y equals ax squared. Now I want to show you that real quickly by looking at some graphs here. So I have y equals ax squared, which is the black graph here. And I also have y equals ax squared plus bx plus c. And you'll notice that they're exactly in the same spot because b and c are both 0. So if b and c are 0, it really is saying y equals ax squared is equal to y equals ax squared. But you'll notice that as I change my b value, I'm going to leave this one here as well. I'm going to change my b value around. It's the exact same parabola. I'm just moving it. So I'm changing where that vertex point is, that lowest point. And as I change that b value, it just moves the parabola. And the same thing goes with the c value. You'll notice the c value just takes my parabola and moves it up or down based on whether I'm going more positive or more negative with that c value. But the parabolas are exactly congruent to each other. And that's what the parabola congruence theorem tells us. Alright, so a little bit later on in this chapter, what we're going to do is we're going to show how this equation y equals ax squared plus bx plus c can help us find key points of the parabola, mainly the x-intercepts, which is something that we don't have a way of finding. Also, it gives us a really easy way of finding the y-intercept. We'll look at both of those a little bit later on. But next what I'd like to do is be able to look at how can we use an application, kind of a real-life application for the standard form for a parabola. All right, one real-life application of quadratics is the idea of gravitational pull on an object, and the formula for that is y equals negative 1/2 gt squared plus v naught t, and this t probably isn't on your notes, so make sure you add it, plus h naught. Okay. Now, what that really means is this g stands for the gravitational pull. So it's going to be either 9.8 meters per second squared or 32 feet per second squared, depending on if you're dealing with feet or meters. V sub 0 or V naught represents the initial velocity or the starting velocity when the time is 0, and H naught represents the starting height or the height when the time is 0. So what we want to be able to do is we want to be able to solve problems involving this right here. All right, let's take a look at an application then of this. Suppose a thrown ball has a height of this right here after t seconds. So this represents the height of the ball after t seconds. We want to find the height of the ball after these seconds, really. So really what we're talking about making a t-table, and we're going to plug each value of t into this equation. Why don't you pause the video at this time and go ahead and do that, and then I'll put the answers on the screen here in just a second. So here's what you should have come up with after you plug those in, and you'll notice that it goes up originally. It starts at 7, then goes up to 33, and then at some point in time it starts coming down, 27, and then somewhere in here it goes below 0. So if it goes below 0, really if you think about that, the ball has actually gone below the ground. So in other words, it's already hit the ground at this point. So conceivably these values, unless there's a cliff there, would not really make sense. Okay? So in relation to the second question here, explain what t comma h, or in other words what those ordered pairs represent when t is 0, 2, and 4. 0, that would represent the starting height, or the value when t is 0 is the starting height. Basically, the value of t equals 2 is saying that, hey, the height of the ball is going to be 27 feet after 2 seconds. And when it's 4, it's going to be 81 feet below the surface that it started at 4 seconds. So if we're going to graph the ordered pairs th over the domain of the function, what I'm going to do is I'm going to go ahead and plot those points. So it looks something like this. Here's the 4 points that we found on our t-table. Now what we want to do is we want to connect those. And you'll notice if I connect those, I really end up with a parabola with a maximum height somewhere just after 1 second, but definitely before 2 seconds. Somewhere in this range here, looks like about right there, is the maximum height the ball reaches. And you'll notice that right here, this point right here, would represent when the ball hits the ground. In relation to this last question, is the ball moving at the same average rate? Well, if it was moving at the same average rate, then what we would know is it would have to be linear. So if I look at the graph of this, I notice that it's not linear. Therefore, the rate from 0 to 1, 1 to 2, 2 to 3, etc., changes over that period of time.